let's try talk about another one. So equilibrium constants now can be calculated from the cell EMF, since we already have a relationship that relates free energy to the cell potential, and we have an equation that relates free energy to the equilibrium constant. Well, these are the same free energies, so we can take this term and say it equals that term, okay? Our negatives cancel out, and then we can simply rearrange the equation to look like this. Now, this 2.3 comes from converting the natural log to the log. Okay, I'm not going to get into the details of that, but if the properties of log, by going from a log base e to log base 10, we simply multiply by e, which is 2.303. Okay. Now, since R and T are also going to be, and F, right? So R, T, and F are constants. We're assuming that we're always looking at 25 degrees Celsius. So that's why we're saying that this is a constant. If it wasn't, we wouldn't be able to do this. We'd have to use this full form of the equation itself. But we're always going to assume that it's at 25 degrees Celsius, and most solutions are very close to that. Room temperature is real close to 25 degrees Celsius. So since this is 25 degrees Celsius, now of course that needs to be converted to Kelvin, because R is 8.3145 joules per Kelvin per mole. So this will be 298.15 Kelvin. And Faraday's constant, of course, is 96,500 Coulomb per mole of electrons. And so that gives us this equation here. So it says that the cell potential is equal to 0.0592. Again, that's 2.3 times 8.3 times 298 divided by 96,500. And that gives us that value there with units of volts times moles per electrons. And then this, again, the N is going to be the number of moles of electrons transferred, and K, of course, is the equilibrium constant. Okay. Okay, so let's try to calculate then the equilibrium constant for the following reaction using the electrochemical values. So first off, if we write this in shorthand form, of course, we have the iron going from iron 0 to iron 2 plus. It was oxidized, therefore it's the anode. It's the oxidation half reaction, or the anode, so the shorthand would look like that. And the copper goes from copper 2 plus to copper 0. It was reduced, therefore it's the cathode. And if we wrote the shorthand form of that half reaction, that would look like this. So again, to determine the E cell, we're going to take the cathode cell potential minus the reduction potential of the anode. Okay, so we'll look those up in tables. And basically, again, we have the cathode, which is this. So this is going to be the copper 2 plus 2 electrons going to copper. That is 0.34 volts in the table. And then we have the, remember, we want to look for the reduction potential of the iron. So it's going to be the iron 2 plus 2 electrons going to iron, and that reduction potential is negative 0.45. So plug that in, and that gives us a standard cell potential then of 0.79 volts. Okay, note that 2 electrons are transferred in this reaction. That's pretty easy to see, right? We had 2 electrons, plus we've done this reaction quite a few times at this point in time. So the number of electrons that transferred or were canceled in the balancing of the equation is the number of moles of electrons that were transferred. So that's N in our equation. So now we can simply plug it in. We determine the E cell, and we determine the value of N. And that gives us this equation here. We notice that the moles of electrons cancel. And so then we have simply rearrange it. We take the 0.0592 divided by 2. That gives us 0.0296. We then divide that by both sides. Okay, so that gives us this expression here. The volts again cancel, and we get 26.69. And we're going to take the anti-log of that. So this is log base 10. So it's going to be 10 raised to the 26.689. And that gives us a value of 5 times 10 to the 26th. And we know that to be true, right? So this means basically, since K is bigger than 1, larger than 1, it is a spontaneous reaction. We also see that with the positive E cell, that this is a positive reaction. And we actually demonstrated it, right? We dipped the nail in the copper solution, and we seen that it was coated with solid copper. And we can see that it is very favored, right? 5 times 10 to the negative 6th. It wants to go until all of the iron in contact with the copper solution has reacted to form the solid copper. So of course the reaction stops at some point because the nail is completely covered in copper, and the copper solution isn't going to react with the solid copper. Okay, so now the free energy change then can also be related then to the reaction quotient Q. And of course, we know the expression for the reaction quotient is the same as the equilibrium constant expression. It's just the products, each raised to the coefficient in a balanced chemical equation, divided by the reactants, each raised to the coefficient in a balanced chemical equation, except of course it's the initial concentrations and not the equilibrium concentrations that we see for K. So if we plug in then for this, again, using our cell potentials instead of our free energies like we had before, right? This time, again, we had the standard cell free energy change. Now it'll be the standard cell potential. And then we had the actual free energy change of the reaction at non-equilibrium conditions. And this is going to be the cell potential, again, that has not yet reached equilibrium. And so now we have this equation here. So this, again, we can simply rearrange. Okay, and when we rearrange it, we're going to end up with this equation. Again, we converted the ln to the log by multiplying by 2.3. Again, we see that we have these constants, 2.3, R, T, and F. So again, we'll combine all three of them, and that gives us the 0.0592 moles of electrons. And so we have this equation here. Okay, this equation is really important, and it's actually called the Nernst equation. So again, like I said, a battery at equilibrium is a dead battery. Okay, it has 0 volts, it no longer works. You would throw it in the garbage and get a new battery. Okay, or if it was rechargeable, you'd recharge it again. Okay, so again, our batteries are always at non-equilibrium conditions. So the Nernst equation, again, illustrates why cell EMF decreases as the cell reaction proceeds. So as the reactant concentrations decrease, the product concentrations increase. So Q increases, thus increasing the log of Q, which in turn decreases the cell EMF, right? So let's look at an example. So what is the EMF of the following voltaic cell at 25 degrees Celsius? Okay, so there's our shorthand form. Again, we know that the balanced chemical reaction, so this is our anode, so it's going to be the iron being oxidized to iron 2+, and it's going to be the copper 2+ being reduced to the copper at our cathode. Again, we've already noted from earlier examples that the standard cell potential for this system is 0.79 volts, and the moles of electrons transferred are 2. Now we need to calculate Q, which is just, again, the concentration. Now remember, in the balanced chemical equation, Q is the product, so in this case, iron raised to the first. Pure solids don't appear in the equilibrium constant expression, then divided by our other reactant, copper 2+ raised to the first. Again, these are the initial concentrations, so we're simply going to plug those values in. And that's going to give us a Q then of 2.5 times 10 to the negative 5th. So plugging all those values into the Nernst equation gives us a value then of 0.93 volts. So if we made a battery out of iron and copper, we would call it probably a 1-volt battery, but the reality is it would be 0.9 volts. Okay. Now let's look at the opposite situation. Okay, so this is E cell, not E cell not. That's our cell EMF or our cell voltage or cell potential. Now let's look at the opposite situation where now all of a sudden we've ran out basically of the copper 2 plus, really. We ran out of the copper 2 plus. It's all been converted to the solid copper. And again, plug those into the value of Q. That gives us a value of 4 times 10 to the 4. Plugging that into the Nernst equation, okay, this then comes out to positive 0.1362, and that now gives us a cell EMF of 0.65 volts. So it went from 0.9 down to about 0.65 when there's almost no copper left. I could graphically show you, it looks like this. So here's our brand new battery. Okay, it always reads, so 1.5 volt battery reads about 1.6 volts, but very, very quickly goes to about 1.5 volts. Now, remember what we said. We said that the potentials are an intensive property, so it really didn't matter how much was there, just as long as there was some there. And this graph demonstrates that, right? So again, the concentration of the, now this is in terms of the concentration of iron 2 plus. I should make it in terms of, I should make it in terms of the copper 2 plus, because that's really what's running out here. In fact, I think this, no, this is going to concentration. This is weird. But anyway, so this is basically what we're seeing here is that the concentration of the copper is dropping, okay, while the concentration of the iron is increasing. But basically, we can see that the battery remains at a constant voltage, and then all of a sudden drops off completely at the end. Again, this is indicative of an intensive property, that it doesn't matter how much is there, as long as there's some there, it's going to have basically the same potential. Now we can see that it's not quite exactly the same. There is a small drop over time, but again, this is why batteries work. Okay, if the voltage constantly dropped like this, it would make our electronics very difficult. In fact, we probably wouldn't have most of the things that we have today if that were true. But again, because it's an intensive property, it basically remains constant until there's nothing left, and then it just plummets to zero. Okay. Okay, now we've talked a lot about a whole bunch of different types of values, and they're all related to the free energy. So the free energy is a really important value in all fields of science and engineering. So we've already seen that we can relate thermodynamic values or calorimetric data to the free energy, right? The free energy was just equal to the change in enthalpy minus the temperature times change in entropy. We've already related it to equilibrium constants. We said the change in free energy equal to negative RT, the ln of the equilibrium constant K. And we've also known that the reaction composition is related. It's just the concentration of the products, each raised to the coefficient in the balanced chemical equation, divided by the reactants, each raised to the coefficient in the balanced chemical equation. And we've also seen the direct relationship between free energy and the cell potential, standard cell potential, and between equilibrium constants and the electrochemical data. Okay, so you can see how all of these things are interrelated to one another. Okay, so all of these things are interrelated to one another. And we'll talk about how in lecture, but E cell then is equal to 0.0592. Now this number comes from a bunch of things that we'll talk about. Includes the temperature and a bunch of other things. So this thing is being good at 25 degrees Celsius. I'll talk about where that number comes, but you need to memorize that number. Divided by N, which again is the number of moles of electrons being transferred in a redox reaction. And then this will be the log of K. And again, it'll be, I'll call it Kc. It's specifically the molar concentrations used to determine K. Okay, so these are for the molar concentrations. And again, this is good at 25 degrees Celsius. At a non-standard temperature, we couldn't use this value anymore. Then we could actually determine what the cell potential of a real battery is at any given time in its life, because we're going to measure the real cell potential. We're going to relate it to the standard cell potential, and we're going to say minus 0.0592 divided by the number of moles of electrons. And by the way, this 0.052, it actually has units. So this 0.0592 is actually volts times, it's volts times moles of electrons. So that is actually the units on this value, okay? And then this is going to be the log of Q. That actually has a special name. That is, this is used constantly in electrochemistry because, again, nothing's ever at standard conditions. So we're going to use it constantly, and it's called the Nernst equation. So this is called the Nernst equation. So this is number 47. It says, calculate the equilibrium constant for the following reaction at 25 degrees Celsius from standard electrode potentials. The equation, of course, is not balanced. So again, what is the relationship between our electrochemical values and the equilibrium constant? So again, that is going to be the standard cell potential is going to be equal to 0.0592 volt mole of electron. And again, that number comes from the temperature at 25 degrees Celsius, converting the natural log to the log by multiplying it by 2.3 and Faraday's constant of 96,500 coulombs per mole of electrons. So that's where that number comes from, as you recall, divided by N, which is the number of moles of electrons transferred in the electrochemical reaction, times the log of the equilibrium constant. So again, we're going to need the number of moles of electrons transferred, and we're going to need the cell potential because we're solving for K. So again, the only way to do that is to balance the chemical reaction. So again, at the anode, again, we have the oxidation half reaction. And at the cathode, we're going to have the reduction half reaction. Now, before I do that, I need to know what is the cathode and the anode. How would I determine what the cathode and the anode is?
Wait, really quick.
Yep.
Sorry, I was writing when you said this, I think, but where did that fraction come from for the E cell not the 0.0592?
Again, remember, that is the value that we calculated from converting the natural log to a log, so 2.3. We multiplied that by Faraday's constant, 96,500, and we multiplied it or divided it by the temperature of 25 degrees Celsius, but in Kelvin, 298.15. So it was just simplifying all the constants, and that's where that number comes from.
Okay.
Okay, because remember, this whole thing was at one point in time, it was relating the E cell in terms of free energy to the log in terms of free energy, right? And that's where we derived this equation from, was the relationships between K and free energy and E cell and free energy. Okay. Okay, so, well, this is the reaction. So I can see that the chromium's going from chromium 3 plus to 2 plus. So is that going to be the cathode or the anode? So the oxidation number is reduced, so that must be the reduction half reaction, so that must be the cathode. Then we have mercury going from 0 to +1 So that's the oxidation half reaction. So that's mercury going to mercury 1. We need to both mass and charge balance. So there's 2 mercury, so we're going to have to put a 2 here. This is 0, this is +2, so we'll have to add 2 electrons to this side. In this case, we have 1 chromium each, so that's good. The charge balance, this is +3, this is +2, so I'll have to add 1 electron to this side. Now, at this point, we could actually look up the reduction potentials in the tables. And so again, there's standard reduction potentials. The mercury has a standard reduction potential of 0.8 volts positive, and the chromium going to chromium 3 going to chromium 2 plus is negative 0.5 volts. So right off the bat, we know that E cell, again, is the reduction potential for the cathode minus the reduction potential for the anode. And so that's going to be equal to our negative 0.5 volts minus our 0.8 volts. And that is going to be equal to negative 1.3 volts. So right off the bat, you should already know something about the value of K. Can anybody tell me what that value is? No? Okay. Okay, so our next step then would be to balance this. So we have 2 electrons, we have 1 electron. Would have to multiply each of these coefficients by 2. So our electrons will cancel. And that's going to tell us that N is equal to 2 moles of electrons. We actually don't need the balanced chemical equation because it's not asking for that. It's just asking for K. And so all we needed was E cell naught and the number of moles of electrons cancel. So now I can just rearrange this real quick. I'll say the log of K is equal to N times E cell naught divided by 0.0592 volt mole electron. So this then is equal to our 2 moles of electrons that were transferred. E cell we just determined was negative 1.3 volts. And this is just our constant. So our moles of electrons cancel, our volts cancel. So that's the log of K. So K, well, let me plug this in, plug that into the calculator. This is negative 43.918. So now K is going to be equal to 10. Since this is just the normal log, it's going to be log base 10. So it'll be 10 raised to the negative 43.918. And that's going to give you 1.2 times 10 to the negative 44. Since this is 1 decimal place, this will be 1 sig fig. This will be 1 times 10 to the negative 44. So there is your equilibrium constant for this reaction. Any questions about any of that good stuff? And again, it makes sense that we have a really small equilibrium constant. Our value for the standard E cell was negative, indicating that it was a non-spontaneous reaction. Of course, in chemistry, that means that the reactants are favored over the products. And the very, very small K value indicates that barely anything went to products, and the vast majority of it remained as reactants. So this reaction really does not occur. Okay. Okay, any questions on that guy? Okay, then let's try another. So this is number 54. It says the pH of a solution can be determined using a hydrogen electrode and any other solution of known concentration. For example, the following galvanic cell could be used. So we have the shorthand form. So at the anode, we have the zinc going to zinc 2 plus. And at the cathode, we have the hydrogen ion going to hydrogen gas. So given that the cell EMF Now, this isn't a standard cell EMF, so this is saying basically this is just E cell. It's not E cell not. Otherwise, it would have said the standard EMF. So it's just saying EMF, so this is just E cell. Then it wants to know what is the pH of the electrode. So any idea of how we would solve this? So since we have non-standard conditions, we don't know the molarity. Of course, we're going to have to use the Nernst equation. The Nernst equation simply says that the E cell is related to the standard E cell, but we have to account for the non-equilibrium conditions. And of course, whenever we count for the non-equilibrium conditions, we're talking about the reaction quotient. So it's minus 0.0592 volt times mole of electron divided by N, the number of moles of electrons transferred, and then the log of Q. So that is the Nernst equation. And so those are all the values that we're going to need. So again, we're going to need the standard cell potential and the number of moles of electrons transferred. So again, we're going to have to set up the oxidation half reaction, which of course is occurring at the anode. And the anode in this case is our zinc going to zinc 2 plus. The oxidation number increased. So that's zinc going to zinc 2 plus. It's already mass balanced, so all we got to do is charge balance it by adding 2 electrons. Now the sum of this is equal to 0, which is equal to the neutral on the other side, which is 0. The reduction half reaction, well, that's going to be the other side. So that's going to be the H plus going to H0, so we can see it's being reduced. So we need to mass balance it. There's 2, and we balance hydrogen by adding hydrogen ions. So we just got to add another hydrogen ion, so that would make it 2. This side is 0, this side is plus 2, so I'm going to have to add 2 negatively charged electrons to this side. Now this side is 0, this side is 0. When we would add these 2 equations, we can see that the 2 moles of electrons cancel, so that means N equals 2 moles of electrons. Now, in this case, we are going to need to balance the balance equation because we need Q. Okay, so bringing all of this down, then we have the zinc, which is a solid. That's going to be important because we're looking at an equilibrium constant. The hydrogen ions will be aqueous. That's going to go to zinc 2 plus, which is aqueous, and the hydrogen, which is a gas. So now I'm also going to need the standard cell potential. So I'll look up the reduction potential for zinc. So again, this is going to be the reduction potential for zinc, which is negative 0.76 volts. And I don't need to look this up. I mean, it will be in the table, but I don't need to look it up because everything is based on this reaction. The hydrogen ion going to hydrogen gas or vice versa. And of course, it is just 0. So our E cell then, so we're going to need this E cell naught. So the E cell naught is pretty straightforward. E cell naught, again, is just the reduction potential of the cathode, which is 0. And then minus the reduction potential of the anode, which is negative 0.76 volts. So E cell naught is positive 0.76 volts. So again, by this alone, we can see that this is a positive value. It's a spontaneous reaction. That means the reaction is going in that direction. But we want to calculate Q. Q is going to be the products minus the reactants. Now, in this case, we're going to have this weird mixed idea again. We're going to have the zinc concentration, and we're going to have the partial pressure of the hydrogen gas. And then we're going to divide that. The pure metal doesn't, pure solids, pure liquids don't appear, so that's not going to be. But then we have the hydrogen ion concentration squared. Now, remember, we always assume that we are keeping this at 1 atmosphere, so this ends up just being 1. It's a constant, so it's not changing, so that's why we can do this, and it doesn't really matter, okay? The zinc was given to us the zinc was given to us as 1 molar. So this ends up being 1 as well. So really all we have is this then. So this basically ends up being 1 over the hydrogen ion concentration squared. So now we can start plugging this stuff into here. So the E cell was already given to us as 0.563 volts. The standard E cell we calculated at 0.76 volts. Then minus the 0.0592 volt mole of electrons divided by our 2 moles of electrons. And then this is the log of 1 over the hydrogen ion concentration squared. So first thing I note is that the mole of electrons cancel. I'm going to bring this to this side, so this is going to be 0.563 volts minus 0.76 volts is equal to negative 0.0592 volts over 2. Then we have this. Now I'm going to do 2 things. First, I'm going to flip this. That simply means this is now going to be a negative value. So this is now going to be negative. And I'm also going to bring this in front. So that's going to be 2. So that's 2 then times the log of H plus. But of course, the negative log of H plus is the pH. The 2's are canceling. So basically, I have this on this side, which is now going to be equal to negative 0.197 volts, is equal to negative 0.0592 volts times the pH. Does everybody see what I've done? Okay, now the pH then, the pH is equal to negative 0.197 volts. And I'm going to divide both sides by this constant, 0.0592 volts. The volts cancel. It's negative too. There's the negative. And then this comes out to be 6.55. No, I'm sorry. This comes out to be 3.327. And if this is 2 sig figs, this will be 2 sig figs. So this is equal to 3.3. Any questions about any of that good stuff? Okay. Okay, let's try another from this chapter. So this will be number 73 from chapter 19. It says, calculate the cell potential of the following non-standard cell. So again, we have a non-standard cell. So again, that means that we're going to be dealing with the Nernst equation. So every time we have a non-standard cell, we're going to be dealing with the Nernst equation. So again, that is just the cell potential is equal to the standard cell potential. And just like we saw before, minus the 0.0592 volt mole of electrons over N times the log of Q. So that's just the Nernst equation. So we'll have to go through all the same things that we just did. So we have to get the oxidation half reaction, the reduction half reaction, which of course is the anode and the cathode. So the anode's always written on this side. The platinum is just, again, since this is a gas cell, the platinum is just what the gas is being bubbled over. So it's just a conduit to the transfer of electrons. So our real reaction is the hydrogen gas going from H0 to +1. Its oxidation number increased. We need to balance that. Since we have two hydrogens on this side, one on this, we balance hydrogens by adding hydrogen ions. So I'm going to have to add another hydrogen ion. Then, of course, we're going to need to charge balance it. So since this is +2, I'll add -2, which means 0, which is now equal to the sum of charges of the other side, which again is 0, since it's a neutral compound. Now on the other side, we have all this weird stuff happening. So it tells you, though, that the cathode is essentially the silver electrode. So that's the silver plus going to silver minus, right? I'm sorry, silver neutral. So its oxidation number was reduced. So that is the reduction half reaction. So that is mass balance. To charge balance it, we just add an electron to it. Now, I'll look up the reduction potentials real quick, because this is the form that it's going to be easiest to see it. Now, this, of course, is going to be flipped, but again, it doesn't matter. That's the H2 going to H+, which we know is 0. But the silver I'm going to have to look up, and the reduction potential for silver +1 going to silver is 0.8 volts. Now we need to add the two equations, but we need the electrons to cancel. So I'm just going to multiply each of these coefficients by 2. Now the two electrons cancel, and again, our N value then is equal to 2 moles of electrons. We're going to need the balanced chemical reaction again because we have Q. So that's going to be H2 gas plus 2 silver ions going to H plus aqueous, and then the silver metal. Okay, so we also have to calculate E cell. And E cell, of course, E cell naught, again, is just the cathode minus the anode. So the cathode was 0.8 volts and the anode was 0 volts. So E cell is just 0.8 volts. So there is our E cell naught value. Okay. Okay, now, well, we need Q. So Q then, Q is going to be equal to the hydrogen ion concentration squared. The metal isn't going to appear there. We have the partial pressure of the H2 gas raised to the first, and then the concentration of the silver ion squared. Now, as we've already seen, this is just going to 1 since it's a 1 atmosphere. Okay, this is going to 1, so that's going to drop out. We're looking for the cell potential. So we know that this is 1 molar. It told us that this was 1 molar. So this is just going to go to 1 as well. But we're going to need the silver ion concentration. How are we going to get that? Well, it already tells you right in the problem. It's going to come from the solubility of the silver chloride. So we have the silver chloride solid going to the silver plus chloride ion. And the KSP for this reaction is going to be the silver ion concentration times the chloride ion concentration. And so we will need to solve this by using an ice table. Or do we? I already know this value. It was given to me. I already know this value. It was given in the standard equation. So that means I don't need an ice table because I already have the values that I need. So it was 1 molar, so that's 1.0, and then the KSP. So basically, the concentration of the silver is just 1.77. So our E cell then is going to be equal to our E cell naught, which we calculated is 0.8 volts. So minus our 0.0592 volts times moles of electrons, divided by our N, which we determined was 2 moles of electrons, and then the log of Q. So that is going to be 1 over our 1.77 times 10 to the negative 10. So basically, I see that my moles cancel. And so if I take 0.0592 divided by 2 and multiply that by the log of 1 over that value, I am going to get I am going to get 0.57731 volts. So E cell then is going to equal the 0.8 minus the 0.57, or 0.2226 volts. 2 sig figs, 2 passed, 2 passed. So 0.22 volts. So that is the actual cell potential of this galvanic cell under these conditions.
In the Nernst equation, why was the concentration of silver not raised to the -2? Because that was what we figured out.
Because the equilibrium constant expression was this.
But we're going based off of
Oh,
Q.
we're going off Q. I'm sorry. You're absolutely right. This is squared. This value is correct. This is squared. I forgot to square that. I mean, this is squared, which means that's squared. It's the same thing, but this would be squared.